Okay, my name is Orvis Evans, and I'm giving a talk called Swimming Upstream, using machine vision to create sustainable practices in fisheries of the future. And don't worry, I won't be reading too many of these slides. So to start off with, I work for a company called AI.Fish. We were founded in 2019 by Jimmy Freese. So the emails to organize this were a little confusing with a couple of Jimmys on the chain. But we are a Hawaii-based startup, and our goals are to apply computer vision to commercial fishing and marine conservation, and give fishermen tools to harvest the right catch sustainably and within regulations. And we service kind of two sides of the marketplace here, the fishers and the regulators and management sides. So we also are trying to give fishery management and regulators the tools to verify that compliance that the fishermen do, and also inform management decisions like when and where to fish and that kind of thing. And we know these folks are not necessarily the most technical folks. So we work really hard to create really user-friendly software experiences for this new blue economy. Uh, I am, there we go. Like I said, I'm Orvis Evans. My focus is on the human interface part, like we talked about. I'm among a team of software engineers, AI engineers, product folks, and scientists who really know the space, know the species, that kind of thing. I'm from Portland, Oregon, and just for fun, I'm a former professional artist who's always kind of worked in that human interface part, but instead of digital interfaces, I did physical interfaces of large scale animatronics, both on land and sea. So fun stuff. So generally, I'm going to focus this talk around why fisheries need AI, and then I'll talk a little bit about our approaches and the tools and workflows we use. So first, why do they need AI? So a blend of industry and regulatory needs. We Fisheries themselves are very commodity businesses. One fishery and the next fishery can both catch the same fish, and really they compete on efficiency. So if we can help that, we help them. And sustainability, that's a huge regulatory interest to make sure that there are fish in the ocean. That's a good interest for all of us. But the industry as well needs to know that there will be fish in 20 years so they continue investing in their business and the industry. So electronic monitoring, I'll talk about that for a minute. So it is a series of, sorry, distracted by the Q&A. A series of sensors, video cameras, GPS antennas, and a computer that are all on board, capturing data about fishing activity. And that we are primarily interested in the video component currently, but there's a lot of other sensor data that can be kind of folded into the work. And all that collectively is called electronic monitoring for fishing vessels. And they are primarily concerned with counting the number of fish that are caught, and detecting fishing effort, and identifying target species, bycatch, and discard. Talk a lot more about that as we move forward. For the last 11 years or so, humans have been kind of reviewing that video footage, reviewing that sensor data, and making reports out of that video review. And that's pretty costly. Electronic monitoring has helped a lot with the cost of this general regulation and counting, because the former approach was having observers on boats with clipboards writing things down, and figuring out who pays for that is complicated and legally complicated and expensive. So making that a video thing that someone can do at home or in an office a lot cheaper. But now with the amount of data, that's a new cost. And as electronic monitoring becomes more standard, we're on track to generate 10 million hours of video per year just for tuna fishing, for example. So it's a huge problem. It's a lot of data to analyze, and it's too expensive to do the way that we do it currently. So AI. So in Alaska, there's a pilot program in halibut and sable fishing to first use electronic monitoring in 2014. And it was installed on 140 vessels to reduce that at-sea observer cost that I mentioned before. And that also helped to improve a lot of oversight where the human observers had to sleep and weren't always on deck. Now you have video cameras that catch every single haul of every single bit of fishing activity. And so that helped oversight a lot. This electronic monitoring became a model for both profitability and sustainability in commercial fishery management. Now it's being applied to vessels in many different regions. So the EU is particularly involved in it and will be moving forward, but also US-based fishing companies and others as well. So that results of that pilot program in 2014, like I said, created a new cost of EM reviewer, even though it reduced the cost of at-sea observers. And each 10-day trip generated 30,000 hours of video, which is a huge amount of video. Uh, Great for oversight, bad because that's just too much data to handle. So that they were having humans go through it and only sample about 5% of hauls, which was statistically useful, but that's 95% of hauls that were not monitored, and thus bycatch and uh, fish that they threw back and different amounts of that were not monitored quite as well as it could be. And I realized I didn't identify bycatch. Bycatch is essentially the non-target species that get caught, and that could be anything from, you're going for blue eye or big eye tuna and you catch yellowfin tuna, or it could be you catch dolphins or sea turtles or different things like that. And each one can have different regulations around how you handle that animal, and how you return it to the sea. So a lot of considerations, and if you're not seeing 95% of the activity, you don't necessarily see all of those bycatch instances. So we were testing AI-assisted EM review, where an AI that we created would analyze the video and do counting of the fish, and then the reviewer would use that as the basis of their review and kind of approve or deny each detection and adjust quantities, but use that as the basis of a human review. So with that, they save nearly 50% of time and costs, which is pretty significant. And for accuracy, there's a very small difference between the standard review and an AI assisted review across 5 trips. There was a 6th trip that we were working on as well, and that had significantly poorer results. And after talking to the reviewers about why that would be, is they were struggling with that 6th result because the AI was detecting a lot of fish multiple times or different things like that, because uh, fish were moving past a bunch of occlusions and the camera angle was just very bad for the AI to be able to keep track of all the fish and detect all the fish in the process that was being done. So things we learned: AI assisted review can be faster, cheaper, similarly accurate. Camera angle and occlusion is important, as we learned, especially with that 6th ineffective trip. And AI review estimates pre-review can be near real time. And that's extremely important because electronic monitoring is often farmed out to third-party companies that are pretty overwhelmed, especially during high fishing seasons. So it can take days, weeks, even months in extreme cases to get results back. So if fisheries don't know how many fish they caught for a few months, it's hard to comply with regulations and only catch the number and species of fish that you're allowed to catch each season, as well as hard to regulate and hard to know how many fish are in what areas, and kind of conservation efforts around that get much more complicated. So estimates near real time is a huge improvement. And further model improvements to our detectors and classifications and uh, trackers can compound the effects. So this trial was about human-assisted review that needed some hand-holding. And as our models get better, that can get either faster or less reliant on the human component, as we've seen over time since then. And as a note, this program didn't include species classification. We expect that component would speed up the review process even more or give more information that doesn't exist in the review process. That's not always part of the human review process because identifying different fish that look very similar is very difficult. And so training people to do that is very difficult. So the three tasks, I give a little preview of those and what I just said for AI in commercial fishing are object detection, object tracking, and object classification. Detection is recognizing given objects within an image, or video in our case. And we're concerned with humans, fish, non-fish animals, and gear or floats. Gear or floats are literally fishing objects that are out in the water. They can help with the other parts of detection or on deck. And object tracking, seeing that an object in this frame, this frame, this frame, and this frame are the same object. If we're counting fish, it's important not to count those as four separate fish, for example. And classification, recognize the class or type of an object. In our case, that would be the species of fish or other animal, non-fish animals. So looking at detection specifically, on the right is a screenshot of our re-review software that shows the AI's results and the timeline that you can scrub through, see the different detections, and adjust them as needed. So detection begins with teaching an algorithm to recognize objects. And this requires a huge data set and a lot of objects in the data set to train the AI model on how to do that. And then splitting the data set into training and then validation and testing components so that a statistical set of them can be used to validate the training set and know that your accuracy, your recall, your everything else is good enough. So detection challenges. All of these are fish. I would struggle personally to identify the bottom right one as a fish, or the top left one, counting the number of fish in that image. Hard to do at a glance. The top right one, shark. Some people don't consider sharks fish, but part of our scope of work is kind of confirming those kind of gray zone areas and defining what exactly we mean by fish and communicating that really well. And another problem is in that shark image, you can zoom in really tiny and see on that shark is another tiny fish. So they look very different, and training a computer to recognize all the different varieties of fish or non-fish animals is a difficult challenge. So things we learned is having more objects for training is better, and the more you have, the better, to a degree. We have 2.5 million annotations in a number of large data sets and counting. And then how we install the EM system can really impact the performance of the AI, EM electronic monitoring. So what we talked about before with the angle being really important. If it's only ever sees the fish front on, that might be difficult to detect more so than from the side. So having multiple angles, different angles can be more or less effective, and having the training data represent the real world data is very important. Further, different types of fishing require fundamentally different approaches to both. And so if you have a bunch of fish caught in a big giant net that gets dumped out on the boat, like this top left one, that requires a very different detection algorithm than ones that come over on a conveyor belt or get pulled over the side one by one. They're each individual large fish. A lot of variation, and you have to train each one. So tracking, that's detecting the fish as it moves across the video or throughout the video. Uh, all three of those are fish. All three of those are the same fish. Like detection, the same fish can look very different in different frames. So we have to use different techniques to make sure we're not double counting fish, and that could be uh, made problematic when people move in front of the fish or the fish moves behind objects, all that kind of stuff. And different kinds of fishing activity are very different for tracking. So, like I said, big net versus conveyor belt versus individual fish are all different. And then how company A and company B culturally work on deck can make a big difference for how effective that detection is, as well as cultural differences across regions and countries and fishing targets and all that kind of stuff can matter a lot. However, good object tracking translates well. So if we solve a lot of those edge cases and a lot of those different routines and variations, that can hopefully, or our evidence has suggested that it can translate really well. And the performance of the tracking algorithm matters. So if we want near real-time results, it can't take a week to process a day-long video, for example. So classification is their third aspect. So, like I said, yellowfin tuna, big-eye tuna, they look pretty similar. The top left is yellowfin, bottom left is big-eye tuna, but we have to classify them separately because they get regulated and caught differently. Training humans to do that is difficult. Training models to do that is also difficult, but once you do it once, hopefully it should be locked in. And we need, like detections, we need a lot of objects of each species to train the models well. But that becomes difficult with non-target species like sea turtles or rare catch instances like sharks or other things that aren't the target thing to be caught, but we really need to know for sure that we've caught them. A lot of difficulties with that. So we've learned that low confidence classification can be okay for the goals that we're trying to solve, as long as we tune algorithms for high recall. Recall is essentially, I'm sure many of you in the audience have better definitions of this than what I'm going to say, but high recall is essentially being okay with false positives because catching more things uh, wrongly is more important than catching fewer things rightly for our use case. Because we need to know that we can catch the rare catch, and despite the lack of data, relative lack of data for those kinds of things. Uh, because bycatch classification is generally more challenging. So tools and workflow. We use a mixture of custom tools and industry standard tools. So for our research data ingest flow, we have a custom service that we've created to normalize our video data to a common format and kind of file organization. The data we get from vessels that we partner with for research can be in a wide variety of formats and organizations. So just normalizing all that is helpful. Our team is distributed across the globe in, I think, 7 different countries. I might be overestimating that. And so having all that in cloud storage is really important. Otherwise, researchers here can't access that data, and that just doesn't work. And from our cloud storage, we get it into a cloud-based 51 instance. That is kind of our central hub for how we organize our data, manage our data sets, visualize them, because that can be important in what we're trying to do, and validate the performance of our models to make sure the detections are kind of what we want them to be, or otherwise look into them to see what are the general problems they're having visually so we can use our gut and our experience to tweak the algorithms to improve. So I'm focusing a little bit on 51 because this is a voxel meetup, but it truly is the source of truth for us and kind of the center hub of our data. So, like I said, we use it for data management, data set management and visualization, performance validation, detection comparisons, like I mentioned. And unfortunately, I can't show a lot of our research data, so I've just used some of the standard images from their website. Hope you don't mind, Jimmy. And we have really appreciated the ability to make custom plugins in 51. We have some specific use cases that we want to kind of stay in that ecosystem or allow our folks to not have to learn new programs and import, export data and that kind of thing. So we use the annotation integration plugin that they've published and have kind of adapted it to our needs. A video clipping plugin, which I'll show you in a second. It's been a great experience in terms of custom interfaces that we can create. And we also initiate and manage our training runs from 51 and also maintain an association between models and data sets, which is extremely important to know what data was in what model. And 51 helps us do that. So this is an example of our video clipping plugin using the video quick start data set. So looking at this video, let's say we only really need a section of the video that we're going to send off to our annotators. So I created this interface where you can drag the handles around or put in specific frame numbers or times, and that clips out a smaller section of the video with a little preview, adds it to the data set, and then we can use the other 51 tools to send it off. And you can see it was created just down there. So, in summary, we are trying to apply this AI to a very specific real world problem. So we want to realize fisheries of the future, where artificial intelligence technology and specifically computer vision approaches, we think they're at a point where they can be applied to support improved fisheries, both for internal data and sustainability of the oceans and their own industry and practices and businesses. So thank you very much. I've appreciated being able to talk to you all today. And there's a link to our references. As Jimmy mentioned, these will go out to you all in that email. So I have not been looking at the Q&A panel at all, so I'm going to give it a quick look over. So first question, are fishermen allowed to sell the legal size bycatch using real-time online auctions automated by the AI app, even if not the primary target species for the ship? I have no idea. Sorry, I can't answer that question. Is data obtained from a specific source and is the data global? So we have a number of partners that we're working with from a few different regions right now. And our target market is a global market that covers about 94% of the ocean. So that's right now we have our data from a few different specific regions, but we are generalizing it out. The edge real-time models should also be adapted to detect man overboard or raise an alert if a particular human suddenly disappears. Oh, that's such a good idea. I agree with that. And actually, that brings up an interesting point. Edge detection of it, the detectors, classifiers, and trackers running on vessel versus in the cloud is a distinction we're making. Our initial push is towards cloud-based work, but we are definitely moving towards and working on options for onboard on edge, especially for regions that have data transfer issues or not enough bandwidth in their island or country. So interesting problems to investigate there. Kyle asks, with video and object detection, are you testing every single frame or every X number? As much as I want to answer some specific technical questions like that, my hands are tied and I cannot. I'm sorry. Uh, you mentioned in one of the slides that bycatch is harder since it's only in a few frames, are having to dynamically adjust how many frames are sent into the model. Um, I think that's pretty related to the first question, but I'll just say it's harder to catch things in fewer frames. What base object detection model did you use for detection? Sorry, I again cannot share that. Did you use off the shield tracker, and or did you have to fine tune a tracker? Um, Unfortunately, a broken record here. Cannot answer that as well. Were the plugins built with Python or JavaScript? Combination. That video clipping one was primarily JavaScript, but we've built them in both. They both work well and they both interoperate really well. Oh no, actually, that video clipping one, I created a component that was that video clipping component, and then created the actual plugin in Python. So them interacting is great. Google also demonstrated AI models that can take a 2D image and generate coordinates of object in the scene, e.g. kitchen cabinets. Maybe this can be adapted to count individual fish. Indeed. Based on training till date, what's the accuracy percentage at? Based on training till date. I don't know if I understand the question, but the accuracy of our models definitely improves with each generation of model that we're working on, both in terms of classification and percentage detected successfully. How do you distinguish the fish types? We work with some scientists in a couple of different universities to help us do the initial classifications to pair with the annotator teams. So we have excellent experts helping us with that.